right, we have everyone here. Good morning, everyone. I'd like to welcome you to our session on the safety the collaboration for the safety of autonomous vehicles. I'm John Currie, Director of Business Development for Automotive at UL. As a global safety science company, UL is highly active in supporting the safe and sustainable deployment of new technologies. In the autonomous vehicle or AV sector, this has included supporting the development of UL 4600, the standard for the evaluation of automated products or autonomous products, which is currently out for comment and is expected to be published later this year. Often at events such as these, I hear about the exciting benefits of autonomous vehicles. But it's really two conversations with ordinary people that really brought this concept home for me. The first, I was on a long flight across country, and I was seated next to an elderly gentleman who was visiting children across the coast. And we had a great conversation which turned to autonomous vehicles. And he asked question after question and listened intently. And it was rather unusual to see this interest in autonomous vehicles from somebody outside the space. So finally I asked him, why the interest in autonomous vehicles? And he said very slowly and thoughtfully, I think a lot about not being able to drive someday. And he was concerned about losing his independence. Wow, something we may all think about someday as well. The second conversation was at a family event. I was speaking to a wonderful lady, and she was an avid supporter of autonomous vehicles, and I asked her about her interest, and she said, well, my daughter, she has brief but frequent seizures, and I'm worried that she may never be able to drive. Wow. So for these people and for many more, AVs can't come soon enough. But how do we do this safely? How do we minimize the risks? How do we minimize the unintended consequences? We know that historically that even much simpler automotive safety products can have unintentional consequences. You know, many of us here may remember the initial deployments of airbags in vehicles and how it was missed, some of the use cases that might occur. So proactively addressing safety is of utmost importance. To explore these topics, I'm very pleased to be joined today by a distinguished panel of experts in AV technology. We have Liam Pedersen, the Deputy Director of Robotics for Renault Nissan Mitsubishi Alliance and Silicon Valley Lab. We have Benjamin Lewis, Director of Autonomous and Mobility Strategic Partnerships at Liberty Mutual Insurance. Mike Wagner, CEO of Educate Research. Sagar Behere, Senior Manager of Highly Automated Driving, Toyota Research Institute. And Miguel Acosta, Chief of Autonomous Vehicles Branch, California Department of Motor Vehicles. So maybe starting with Miguel, would you introduce yourself and say a few initial words?
Well, good morning, everybody. Thank you, John. As John mentioned, Miguel Acosta, I'm Chief of Autonomous Vehicles at the California DMV. And you could be wondering why California DMV is on the stage here with these other distinguished guests. And we actually administer the program that oversees the testing and permitting of all of the companies that are testing autonomous vehicles here in the state of California. We currently have, I think, 66 now. We just added an additional company, 66 companies that are testing on public roads here in the state of California. And since the inception of the program in 2014, these companies have traveled a little bit over or close to 7 million autonomous miles here in the state of California. So again, my team oversees this testing, and we'll talk a little bit about that in our discussion today, and I welcome any questions that you may have. Thank you.
Good morning, everyone. Thank you for inviting me here, John. My name is Liam Pedersen, and I'm the Deputy Director at the Renault-Nissan-Mitsubishi Alliance Lab, which is down the road. This lab has been there for the past 7 years, and I was originally brought on there to start the autonomous vehicles research effort for Nissan and now the Alliance. Prior to that, I was actually working on very different kinds of robots, ones that moved very, very slowly and did not interact with people because they were on the surface of Mars. And so that was a lot easier in some ways. But autonomous driving it's a fascinating problem. I think it's one of the grand challenges of our time, and it's amazing how much progress that we're making right now. And thanks to the initial efforts from the DARPA Grand Challenge, we now have this entire ecosystem of sensors and algorithms and other components that are allowing us to bring this technology to market. But we're still facing serious challenges in how to maintain safety while also being socially acceptable. And let me get back to that in a moment. We're still having trouble bringing down the cost. If adding a $30,000 LiDAR to your customer car is not very attractive for most people. And finally, because these are embodied systems operating in our society in very complex situations, certifying them is going to be very difficult. I will yield to you on that, and I'll yield to my colleagues. So let me just quickly comment on what does social acceptability mean for a vehicle? Well, first of all, the obvious part is be safe, don't hit things. It's very rude to actually drive into somebody. But we can be safe by standing still or driving very, very slowly, and that's not socially acceptable either. We need a car that is efficient, and yet when it does make a move to either avoid someone or make some other change in its course, it needs to be explainable so that other people can predict what the car is going to do. A large number of autonomous vehicle accidents are actually the vehicles being rear-ended by other drivers because it does not react in a way that a human driver behind can actually understand and predict. And then finally, in our roads, we frequently find very complicated situations that is very hard for AI to deal with. For example, when I was driving earlier, I came across a traffic light with construction. It was a red light, and the construction worker is doing this. Now, what is a machine meant to do? In fact, is that a decision you really want to trust to a machine? And for that, I'm a big favor, largely in favor of using human guidance, a form of teleoperation, bringing a human into the loop, a remote human into the loop, to just give a little bit of hints, a little hint for these difficult situations, so your vehicle doesn't get stuck. I do not want an autonomous robotaxi stuck in the middle of New York City and making the citizens angry. And with that,
Thank you, Liam. Sagar.
Thank you. My name is Sagar Behere, and I lead the systems engineering and safety activities at Toyota Research Institute. TRI is the part of Toyota that is developing technologies for highly automated driving. And not only are we engaged in pushing the frontiers of what is possible, but we are also looking at harvesting this technology so that it can be deployed safely at scale in a variety of ways. So both applying it for the kind of operations where you as a driver will push a button and you can go to sleep and the car will take you where you want to go. That is one application, and we know that there are significant challenges. But on the road to addressing these challenges, we think that there are low-hanging fruit. So, for example, something that the gentleman mentioned earlier today was, why don't we have cars that detect when the driver is about to fall asleep? And we think that this is a classic low-hanging fruit. Can the vehicle detect that the driver is in fact incapacitated and come to a safe stop, maybe warn the other vehicles that this vehicle is incapacitated? And we think solving this question is a step on the way to developing larger automated driving technologies. But this one particular feature is potentially simpler than developing a car that can drive itself in every conceivable situation. So at TRI, we push the boundaries of what is possible, but then we also push small pieces of technology to our parent company, Toyota, so that it can be brought into deployment as early as possible. My own background is that I've been developing complex safety critical systems for about 15 years now. And after making endless exciting demos, I started realizing that there is a critical piece that is missing in order to take these really, really cool technology demonstrators and deploy them at scale. And this missing piece is, to some extent, safety. And in order to achieve the level of safety that we want, it also needs a change in the way we develop these systems, which is systems engineering. And the challenge of safety and systems engineering is twofold. People usually tend to focus on either the one or the other. The first aspect of the challenge is the raw technology. And that is something that I think we'll discuss a lot, so I won't talk much about the technological aspects of safety. But the second aspect is strongly related to culture. The kind of systems engineering and safety that you would find in the defense field or in the traditional automotive field is typically something that would be very hard to digest in a fast-paced Silicon Valley-style startup. And so a story that plays itself over and over is the software exists long before safety and systems exists. The company starts facing problems, and the wiser ones realize, hey, we need a systems team or a safety team. So they go out and hire a lead to build that team, and that is exactly what happens. But when the systems guys start coming and talking to the machine learning people or the software people who were there from the very start, there is often a question, well, who are you again, and why should I listen to you? And handling that in a organization that is, very large, over 200 people, requires a set of skills that is almost entirely orthogonal to the raw technical skills that you need. And both of these are extreme challenges that we must solve in order to realize the benefits of this technology. So I hope we'll have a stimulating discussion today. And with that, I'll give the mic to Mike.
Thanks. I'm Mike Wagner. I'm the CEO of Edge Case Research. We're a startup company based in Pittsburgh, most of us coming out of Carnegie Mellon University. So just to add to what has been said already, and I don't envy Ben for having to go last because those were really good intros. I guess I kind of wanted to frame a little bit of where we are before we start talking about collaboration, because I do wholeheartedly agree with what was just said about trying to bring these different groups together, and basically that's a reason for collaborating on this topic. But sort of another trend is that we need to be able to pull together some of these autonomy and machine learning capabilities into the sphere of traditional safety engineering. And I think actually if you look at how technology has been developed, and it's shocking to say that I've been at it now for 20 years, you can see an interesting trend. So the first project that I started working on in the late 90s at Carnegie Mellon with Liam actually, built a robot that traveled through a desert. It was one of these NASA projects that Liam was talking about, and it was moving very slow. I don't know, 25 centimeters a second or something. That was cutting edge autonomy at the time. And there are several people in the room that realize that 20 years really isn't that long of a time to go from cutting edge at 25 centimeters a second to cutting edge being at 100 kilometers an hour or something. And to bridge that gap, there's been a tremendous amount of technology that's been needed along the way. Folks like Liam have done quite a bit of work in the world of machine learning and classification and autonomous driving and navigation. And thanks to a whole community of people, we've gotten to the point where I think it's a lot more than just a demo. I think we're actually able to show the capability be fairly robust. But just like my co-founder Phil Koopman likes to say, there's safety, or there's safe, there's unsafe, and then there's something in the middle. And I think actually right now the technology is somewhere in the middle, in the best cases. And what we're starting to see now are groups like EdgeCase, like some of our collaborators and like some research at universities, that's actually taking some of these same kind of robotics techniques and applying them specifically to this problem. So we kind of had a first wave of kind of understanding how to build the system, and now we're seeing a second wave, which we're proud to be a part of how you can build the system so that you can really show that it's safe. And so that's a pretty exciting time for us, and as I said, we're very glad to be a part of it. So thanks for your attendance, and I look forward to the discussion.
Thank you, Mike.
Thanks, Mike. So Ben Lewis, I am a Director of Automotive and Mobility Strategic Partnerships at Liberty Mutual Insurance. Liberty is about a 110-year-old insurance company with a long history of being a global leader across many different product lines, one of them being auto insurance, and I think we'll touch on that a bit as we get into the conversation. But you know, kind of looking at that history, you know, we're seeing a major change and transformation in the automotive space, which is a big part of the, you know, a big part of our business and the insurance industry overall. And what we're doing is keeping pace with that change. And you know, again, for over a 100-year-old company, that's a pretty big deal. And what we've done is I am part of a practice that focuses on the sharing economy and new mobility business models and technologies. And we have dedicated underwriters and dedicated claims folks and other dedicated professionals who focus on autonomous vehicles and you know, ride sharing and car subscription and all these new technologies and business models that are changing the way that we move from A to B. So that's a little bit about why we're here and why we're interested. We sit on the panel for UL 4600, so we've worked with John's colleagues on that, and then we also are partners too and investors in EdgeCase Research, so we know Mike and his team very well. Just quick step back, I guess I could talk, you know, I can't match the technical capabilities of the panel, so I won't try to. But I guess to maybe tee up the fact that we're talking about collaboration, there's sort of two ways that I think about it. It's come up on panels I've been on in the past, and typically the way that we've talked about it when I've been in other venues is looking at the consumer and looking at public acceptance and how we can drive collaboration and enable collaboration to get this technology that could, you know, has great potential benefit to be adopted by the public. And you know, I think that's on a personal basis, that's where I come from when I look at the topic of collaboration in the space. How can we, you know, as a company that has a large consumer population, participate in this change to enable and sort of unlock it for the broader public and ensure that, you know, we're doing it so that it is safe and it is socially acceptable at the same time, and success is a result of that. So I think we could maybe talk a little bit about the consumer side of this as one piece of it. The other way we think about collaboration as an insurer is that it's a driver of the complexity in this space. And by that I mean that the automotive industry becomes a lot more complex and intricate when we are talking about autonomous vehicle technology. And for us, looking at insurance and risk and exposure, that means that those items, those topics, you know, insurance, risk, and exposure become complicated as well. And we have to think about how the complex value chain and the collaboration and the contractual arrangements and all of these things that are now you know, coming to fruition with autonomous vehicles impact liability. So again, that's another thing we'll probably talk about. But it's necessary, and we're very much, again, a part of that collaborative environment that is critical to bringing this technology to market effectively. But it also brings some considerations that we have to think through as a stakeholder in the space, and things that we like to you know, research and analyze so that we can bring thought leadership and support back to the folks that are actually making this happen out on the roads.
Thank you, Ben. Let's start with Liam. Maybe pass the mic down there. To tee us off, Liam, could you please walk us through some of the major systems of autonomous vehicles, touching on the role of sensor systems, especially LiDAR and cameras? What are the important aspects of the different sensors in terms of providing for the safe operation of autonomous vehicles?
Well, So an autonomous vehicle, the fundamental thing of an autonomous vehicle is it's a robot. So you have sensing, and then you have some kind of perception that takes out, extracts meaning from your pixels, your range values that you get from a LiDAR or radar returns, and actually extracts meaning from them. So there is a pedestrian, there is a car, this is the surface of the road. And then you have to fuse that into a consistent, what we call a world model, which is the vehicle's view of everything that's going around it. There are cars in that lane, they're all traveling in that direction, that pedestrian is crossing and they appear to be going in this direction, they appear to be crossing the road, and this is their predicted path. So we really like to be able to predict what the other agents are doing and what their intentions are, because we're going to interact with them. And that is where decision-making comes in. And that is the logic of, when do I go to stop sign? Should I overtake? How do I follow the road? And then that gets passed on to control, which is responsible for basic obstacle avoidance, not hitting things, and then turning the wheel. Now, you mentioned sensors, and I strongly believe that for safety, we do need a diversity of sensors. But first of all, I've got to say is that vision is the most essential sensing modality of all. It is the only one that we have right now which has the pixel density that allows us to identify not just that there is something on the road, but what it is. And I want to know, is that a child? Is that a person? What direction are they going? Because I want to understand their intentions. I'm going to behave very differently towards a pedestrian than I would towards a lamppost that's in the middle of the road, for example. One I go around, the other one I yield to. Nonetheless, vision does have shortcomings in the machine learning, and the techniques for analyzing vision are still not quite good enough to give us the reliability that we need. It has difficulty working at night and in poor weather conditions, and so we need sensors that can overcome that. I'm very much in favor of LiDAR. Sorry, Elon Musk, but LiDAR gives us something with great density and allows us to tell, is there something in front of the car? Don't hit it. I don't know what it is, but don't hit it. And we're able to process LiDAR using non-machine learning techniques. So we can do geometric reasoning to understand where the load-bearing surface of the road is, where other objects are. And so we have a parallel pathway besides from machine learning and vision to do that. And then, of course, radar would be a great sensor as long as we can get the resolution of LiDAR. It's very cheap. But at the moment, it's still not as robust as LiDAR for that high precision sensing of the environment.
Thank you. Let's go back to Ben here. Ben, who owns safety for autonomous vehicles? Is it the OEM, vehicle owners, operators, insurers, regulators, all of the above, none of the above?
I mean, it's an easy answer, but I really think it's essentially all the above. And this is touching on the complexity I brought up earlier. I mean, in a simplistic view, the automotive value chain in a traditional world is, someone manufactures a vehicle, they may have some upfitment or something that happens after the fact, but then it generally will go to a distributor, it'll be sold to a third party, and then that third party will operate the vehicle. That's either a consumer, and an individual who owns the vehicle themselves for private use, or a commercial operator who might have a fleet that they rent out or they provide to employees or conduct business with. In that case, as liability tends to fall on the operator. In today's world, the way that we have constructed our liability framework, the human in the driver's seat, 9 times out of 10 is going to be responsible for whatever outcomes there may be. And if there's an unfortunate outcome, if there's a loss, they tend to be at fault for that. In this new world of autonomous vehicles, again, the value chain becomes a lot more complex. You have a vehicle manufacturer, but now you're going to have hardware and sensor manufacturers who contribute to that base vehicle platform, and then you're going to have software providers who contribute on top of that. And then you may have business models that crop up that utilize those autonomous vehicles in different ways. And some of these business models are here today. You have, ride-sharing services and car sharing and car subscription and other ways of providing transportation to folks in a model other than personal ownership. But with autonomous vehicles, a lot of those models get sort of accelerated or unlocked in different ways that aren't really available when humans are behind the wheel. So, for the insurance industry, we look at that and we say, each step in that value chain, and I'll get back to why I'm being specific about it being steps, but each step in that value chain, has a responsibility associated with it. And safety is one of those responsibilities that those entities or those steps, will have to be cognizant of. The reason we look at it that way is that there's, organizations will group those steps in different ways. So there's organizations that specialize and they may only create hardware components and they have certain level of, safety that they have to be aware of and a certain level of responsibility. And then there are organizations that are, grouping steps in the value chain together to do multiple things. And they have a higher sort of standard of care that they might have to uphold and a higher degree of focus on safety that they might have to be cognizant of. So that's kind of how we're viewing it in the insurance industry is that, again, things become more complex and there are pros and cons to that. But it's more of a consideration that we have to keep in mind when we think about how liability and responsibility are delineated or sort of doled out along the value chain.
Very interesting. Let's pass this now down to Sagar. We all know that automated driving needs to be very safe. But what is very safe? What are some of the approaches to deciding how safe is safe enough?
Well, if I could give you a single number for how safe is safe enough, I probably wouldn't be here. What I can tell you, though, is there are a number of approaches that are used both within the automotive industry as well as other safety-critical industries for deciding how safe is safe enough. And I'll run through some of those approaches, and I will also give you my thoughts on how this might eventually pan out. So the naive way to crunch numbers for safety is to ask yourself, what is the fatality rate due to automobiles today? And it has stayed roughly constant at about 1.2 million globally for the past few years. So 1.2 million people die every day because of automotive incidents. Not every day, every year. Small difference. And so is it sufficient to say that as long as automated driving results in fewer fatalities, that is acceptable? And this is not actually the case. As humans, we are far more forgiving of the mistakes of other humans than we are forgiving of the mistakes of machines. And so if you give this problem to an engineer, maybe the engineer would go, well, okay, then what's the fudge factor you want me to apply? Should it be twice as safe, 10 times as safe, 100 times as safe? And I'll answer this question before I hand back the mic. But I do want to talk about what are some of the approaches used by other companies, for example, other domains like railways or nuclear industry, when they create technologies that have a vast potential to benefit society, but inherently carry risks. So one common acronym you will find if you Google for this is ALARP, which stands for as low as reasonably practicable, which basically tells you that the risk posed by introducing a new technology should be driven to a value that is as low as reasonable, where reasonable is still somewhat vague, but it's the point where you reach the point of diminishing returns. The amount of resources that would be needed to be invested in order to gain safety would be grossly disproportionate to the amount of safety you will actually get out of it. Another method that is more popular in Europe is called minimum endogenous mortality. So what this says is, for a given age of the population, say 4-year-old children, what is the natural fatality rate? And you make arguments that the new technology that you're introducing will not increase the fatality rate beyond what this natural mortality rate is. And this is one way of doing it. Many of the projects in Europe, like the recently concluded Pegasus project, strongly used an indicator called minimum endogenous mortality 20 as a way of making argumentation. But really coming back to the notion, and then there's others. There is one called GAMAB, which is French for globally at least as good, which says that the new technology should not increase the risk compared to the existing situation, and there are ways to measure the risk of the existing situation. But coming back to the notion of 1.2 million lives lost per year, ultimately, we at Toyota believe that it is society who has to decide what is acceptable and what constitutes society. Is it you? Is it me? Is it the person who enjoys the benefits of that technology? Is it the person who stands to be injured from that technology without getting its benefits? This is a complex question, and it actually varies from region to region. The way the government authorities and regulators and engineering companies work together in, say, North America is different from Europe, which is different from Japan. And so this question will pan out in a very interesting way. But there are other domains that have considered disproportionate benefit versus risk. So in the US, if you look at vaccines, this is a classic example. Vaccination leads to benefit of many, but it still poses risk. As new vaccines are introduced, there is always the possibility of some fatalities from the vaccines. So how do we treat this? In USA, there are the so-called vaccine codes, which are used to redistribute the risk in the population, somewhat similar in principle to how the insurance companies operate. So maybe Ben will have more to say about it. But in the end, I want to leave you with a question. People often talk about the so-called trolley problem, and people talk about ethics. There is one question that definitely needs to be considered by any system of ethics. And that is as follows. We know that this technology is unlikely to be perfect out of the door, but it does bring benefits. So if there is some technology that saves X lives every year and takes Y lives every year, at what ratio of X to Y can we as society justify launching this technology? If there are going to be 2 people killed by this technology every year, but 100 people saved, is that worth doing? Or if there are 2 people that will be killed, but 1,000 people saved, is that worth doing? So that is also something to dwell on. Thank you.
Interesting questions. Let's stay with you, Sagar, for a follow-up here. In automated driving, or AD, is this a natural extension of ADAS? And for the non-automotive people, that's advanced driver assistance systems, correct? Yeah, that are common today. There are arguments going both ways, that AD is just better ADAS, but also that AD is a step change away from ADAS. What is your opinion?
Well, the true answer is, yes and no. But I will explain what the arguments are for either case. This question, it arises from a very fair and natural way of thinking. Back in the day, we didn't have automated safety features. But then, if you look at it now, we have automatic emergency braking, which applies the brakes in case you are about to rear-end someone. We have a blind spot monitoring system that tells you if somebody is in your blind spot as you intend to make a turn. We have front and rear cross-traffic alerts. We have lane keep assist systems that nudge the steering wheel so that you can stay in your lane. And so a natural question to ask is, if you take all of these distinct driver assistance technologies and put them together and just improve each one of them slightly, will you get full self-driving? After all, for the vast majority of cases, if you can stay in your lane and not hit the car in front of you, that's already quite good, and it's something that we are seeing. So the question then is automated driving, AD, a natural extension to ADAS, automated driving assistance systems? And in theory, in terms of the pure functionality, yes. All the features that are present in ADAS systems today will be present in future automated driving. Automated driving, in this sense, will be a superset of the capabilities of the ADAS systems. The way in which AD and ADAS differs is what is the underlying technology used to deliver these features. Today, the ADAS systems are quite fragmented. You will go to a supplier who will have their own radar and their own electronic processor for the radar signals. You mount it at the corner of the vehicle, and you have a blind spot monitoring system. You have a different supplier using a different technology, maybe a forward-looking camera that gives you lane keep assist. And so the way the business and technology has evolved is you have all these fragmented systems that are present in the vehicle, and it's becoming very, very difficult to cohesively knit them together as an integrated whole. And so from a business and technology perspective, there isn't a natural path to proceed from ADAS to AD. But we can make clean sheet AD designs that we can then have the same features as ADAS. So I can create a system that has a lot of sensors, a centralized powerful compute unit that can recreate the functionalities of ADAS, and then as the technology develops, take those ADAS functionalities and start adding AD functionalities on top. And so the short answer is, in terms of pure functions, AD is a natural extension of ADAS. In terms of how these systems are designed and developed in terms of the business and technological ecosystem, they're very different.
Thank you. Let's go to, oh, absolutely.
Yeah, I'm sure Sagar will agree with this too. It's also interesting to think about the difference in sort of the safety guarantees and the safety case around these two different systems. So for example, and actually what I'm about to say is one of the reasons why I really like Toyota's approach, because if you add more safeguarding capability to sort of help the driver in tricky situations, then if you avoid any accident, you avoid is an improvement, right? So let's say that you have some kind of emergency braking function that works half of the time, right? And that's then in that case, if there's a human in the loop and this is an ADAS function, then that's 5 accidents, that were avoided, very loosely speaking. Whereas if you flip that and turn that into a fully autonomous vehicle, now that's 5 accidents that occurred, right? And that's a problem, because the number that you need to get to there, tying several of the questions back together, is going to be very large. It's not just 9 out of 10. It's not just 999 out of 1,000. It's going to have to be basically all of them that you test. And that's a very, very big challenge. But if we're starting with technology that we have today, we can apply that today and get real benefits, which is, I think, again, a really nice thing about your approach.
Yeah, thanks for bringing that. I'm happy to share a little bit of the Toyota strategy here, but imagine for a moment if you had a sensor, hardware, and software system that, in theory, is capable for full automated driving, but the state of automated driving technology is not yet at a point where you can, just flip the switch and say, this car will drive anywhere, anytime, no restrictions. But you can use the same architecture, you can use the same hardware and software for what we call a super ADAS system, or in Toyota parlance, it's called Guardian. And this is AI that is watching the road as you are driving. It is identifying threats, it is making assessments, because at the end of it, ADAS and AD both still need sensing, both still need perception, both still need planning, both still need control. So the question really is, can you take this highly capable system and initially deploy it so that it is only acting in very limited contexts? It does the detect, inform, warn, the driver is still responsible, and in extreme cases, when the system has a lot of confidence, it can intervene. For example, it can do an automated emergency braking. So it acts in a do no harm paradigm, and by doing this, we can learn from real data, which we can then use towards fully automated driving. And so the advantage of ADAS is it only kicks in when the situation is already bad, and it can be tuned to avoid harm. Whereas with AD, it is a 100% duty cycle, and it must never fail. A much tougher challenge.
Yeah, that's a good point. How similar the capabilities, but how wide the gap in performance that's necessary. Thank you for that discussion. Ben, let's go back to you. How is safety measured, and how will vehicle insurers quantify the risk?
Yeah, I mean, I think some of this remains an open question, and in fact, it's something that we're working on in our partnership with EdgeCase, and we actually see a lot of value in what UL 4600 is going to do in bringing a framework for that discussion. I actually think it's a decent segue because one way we measure safety is and sort of the impact of this technology is the losses on roads, and for us. The loss of human life or injuries being caused by auto crashes is clearly one of the biggest negative impacts we see on the road, and one that we obviously want to combat with this technology and with advances in automotive safety. The other thing that, and we actually had a little conversation about this in one of the first UL 4600 meetings, but the other thing that we think about in the insurance industry are all the other losses, sort of the economic and financial losses that occur. I mean, if we imagine a sort of utopian world where autonomous vehicles actually result in no fatalities, but they cause property damage every other day, I think people are still going to have a hard time accepting the technology. So, for us, it's we also measure this by sort of the economic and financial loss that society incurs, and that is absorbed in at least in part by the insurance industry to help offset those losses on an individual basis. So I think that's kind of one measure that we have it already. It's existed again for hundreds of years that we're using to look at how the technology is impacting society in a positive way. But as I alluded to at the beginning of the answer, there's more to do there, and we are looking at all sorts of metrics to try to get at what specifically constitutes safety with this technology, because it does change, particularly when you're talking about automated driving, it does change the equation significantly. And there are many sort of attempts out there. There's a lot of work underway to define the measures. There's been there's the RSS framework from Mobileye. There's metrics in states, including California, around disengagements. There's lots of healthy experimentation, I think, happening to define what those measures are. And I think we are getting close to the point where the scale of deployment of autonomous vehicles will sort of bring in the data necessary to land on concrete, statistically significant measures that insurers and others can use to define safety.
Thank you. Let's go back to Mike. Is the AV technology as safe as we can measure? Or asked another way, is it possible to simulate and test our way to zero risk?
No.
Thought that might be the answer.
Next question, please. Yeah, no, I'll give you the more maybe useful answer to that. I think it's been said a couple times up here that there's going to be some amount of risk. I mean, for one thing, there's going to be some level of risk, and that's going to be counteracted by an increase in utilization if these guys do their jobs, right? So, I might actually be carried, and exposed to more miles per year than I am today if I can, work on my way to a meeting in D.C. and work on my way to a meeting in Detroit, because Pittsburgh is halfway between both of them, right? Okay, so I think there's definitely going to be residual risk, as the safety engineers like to say. It really all does come down to the actuarials, like Ben was saying, and one of the things that we want to try to offer in our products and in our techniques is ways of getting to leading measures of that, because that's really the question that we're facing here, right? Is if you take a version of autonomy technology that is being fielded, right? You don't want to have to wait to see the actuarials, especially if there's something bad about that. And so what EdgeCase is really trying to do, since we're speaking to an ML and AI audience is really kind of a regression analysis to be able to say what measurements can you take up front that are actually meaningful predictors of your actuarial data once it gets fielded. And that's a tough question. It's not just simulation and testing up front, although that is an important part. It's also watching how they work on the road, which I'm sure you guys spend a lot of time doing as well. And defining what you're watching for while you're out on the road is actually one of the really exciting things about the UL 4600 standard.
Yeah, that makes sense. And I can imagine that initial deployments being smaller may help lead to learning and promote larger deployments later.
Absolutely.
Let's move down towards the end a little bit more. Let's go to Liam. From your perspective, what is the role of simulation for ensuring safety?
Yes. No, simulation, of course, is it's essential for that. And so there's the obvious reasons. There's a lot of things that we can simulate that we cannot, or rather, I should say, we should not try outside of simulation. So situations that put other people in danger, for example, we would only want to do that in simulation. But more importantly, simulation allows us to do testing on a massive scale. So we can run hundreds of thousands of simulated runs for different situations, which we cannot do inside, testing a vehicle on the road. But the question, I think, is what is simulation actually really good for? As Mike said, it's not good enough for everything. It's very good for testing the decision-making of the vehicle and testing the different confluences of other actions that can happen. So the different arrangements of the other actors, you can test those large number of arrangements. It is increasingly being used to also test perception systems. And that is very interesting, because if we can use simulation to test the perception system, now we can test a scenario in a diversity of weather conditions. Sensor failed in one area, in one place. Now we could try to isolate what causes that. But I still think we have to be very careful doing that. Perceptional data is very hard to simulate accurately. And I still believe there is no such thing, there is no substitute for the real thing. So I think I would then like to sort of conclude is, what is the general framework as how you should use simulation? It has to be part of an integrated test with real data. I'm very partial to the idea of, or the practice, I should say, of when you have a large fleet out in the wild being tested, every time something occurs that is a potential failure, not only a failure, but a potential failure, if you can recreate that situation in simulation and then decide, would it really have been a failure? What caused that to actually be a failure? Was it the arrangement of other actors? If the other person had been driving slightly slower or the pedestrian had been behaving differently, would that have caused a problem? And the reason I think it's so important to use real-world testing in order to seed your simulation is because fundamentally the ultimate difficulty we have with simulating is enumerating all the possible use cases. We just have a combinatorial explosion of the number of different arrangements of everybody else. Now, not all of those use cases are going to be dangerous. Most of them are irrelevant. But if we can use our practice, and then if we can build our system to continuously improve, continuously gather data from the fleet of vehicles, and then continuously use that information to create more scenarios and improve the simulation as time goes on.
Thank you.
Can I add just one?
Yes, quickly.
Yeah, so someone who's going to present later today talked about the need for machine learning is because of ignorance, and there's another one, ignorance and laziness. So this group is definitely not lazy, but one of the biggest reasons why we need to do the monitoring that Liam is talking about is because of the ignorance we have about all these edge cases out in the real world. I had to say edge cases, sorry.
Thank you. Let's go all the way down to Miguel. with so many companies experimenting with autonomous vehicles and testing on public roads, from a regulatory perspective, what is California's approach to safety?
Yeah, so just to add to the panel members, so when we're talking about collaboration, I think motor vehicles and state government as a whole, we wanted to create a framework for innovation. We wanted to create a space by which companies can come in and test this in a safe manner. One of our charges in motor vehicles is the safe operation of vehicles on California public roads. So in 2012, Senate passed a bill to create 38750 in the vehicle code, which allowed for us to actively permit some of these companies. In 2014, we created our first set of regulations that allowed companies to come out onto the roads, and this allowed for companies to test with a safety driver. So as I mentioned earlier, we have 66 active permits right now. And of those, we have a little over 800 vehicles statewide and just over 2,700 safety drivers. And each one of these companies right now that's testing has safety drivers behind the wheel, ready to take over. And one of the some of the data elements that we capture in that particular permit with the safety drivers are two things. So if the vehicle is in a collision while it's operating on California public roads, they have to report that collision to my team within 10 days. And then the other bit of data that we collect each year is something called our annual report of disengagements. I think one of the panel members mentioned that. So this occurs when there's testing occurring on California public roads where the safety driver determines that there's some kind of situation that where they need to intervene. So they take over from the ADS, and each manufacturer has to describe the circumstances associated with that. So in 2018, we issued our second set of regulations, when I'm talking about framework for collaboration, to allow for driverless testing out on California public roadways. This would allow for companies to test without the presence of a safety driver. And then in this last year, we had a third set of regulations, which now allows for autonomous delivery services as well. So there's three permits that manufacturers can have. There's the testing with a driver, testing without a driver, and we also allow for the commercial deployment. And I just wanted to note in the space right now, again, all 66 companies are testing with a driver behind the wheel. We have issued one permit to a company to test without a safety driver. That's one company out of all the 66. And that company has yet to start testing without a driver behind the wheel. So in terms of collaboration, one of the things that I really try to do is I try to work hand in hand with the companies. This is an incredibly complex question that we're working with in terms of how to measure safety, how safe is safe. And I think it's up to the manufacturers and the regulators and the insurance industry and all of us to partner together and have these discussions within the framework that we created.
Thank you. And as we're starting to get a little low on time, I want to turn to a rather intriguing topic of machine learning and autonomous vehicles. Traditionally, with automotive systems, the engineers design them, and the controls are set and they don't change their behavior over time. But now with the advent of using artificial intelligence and machine learning techniques for control of these vehicles, that opens up some more complex possibilities of the vehicle changing its behavior, and how do you assess that for safety? So let's first go to Ben. The potential use of machine learning in some AI algorithms means that an autonomous vehicle could potentially behave differently over time or differently than when tested in certain situations. So if AV algorithms can learn and self-modify, how will insurance be administered over the life of the vehicle?
Yeah, it's an interesting question. I think one thing that comes to mind is just that, so we've talked a lot about how autonomous vehicle technology and automated driving will change the fundamentals of the automotive industry and of the sort of the other use cases that we've touched on. I think the other side of this that I always try to keep in mind is that there are just some aspects of this that don't change. I was actually at a conference once, and they were doing a mock trial of what would happen if there was an autonomous vehicle crash with, fatalities and other major losses. And they got to the, I think it was an officer in the Michigan State Police, and they said, how would you investigate this autonomous vehicle crash differently with all this technology that's involved now? And he would say, I wouldn't. I wouldn't change a thing. I would go to the accident scene. I would, put down my lines. I would conduct my sort of physics, investigation, whatever it may be, to make sure that I understood the way that the scene played out. So I think that was a reminder, one snippet and one reminder to me that some things don't change. And the reason I mentioned it is that this is, in some ways, we don't have to think about this differently. When we're insuring a driver today, your behavior changes over the course of your life. We don't underwrite and price a 17-year-old freshly licensed driver the same way we do a 50-year-old driver that has many years of experience or that operates in an urban versus a rural area. So there's many ways that we account for this today that will probably remain in the future, and we'll continue to use those methods in the future. I think what does change is data, and the fact that these vehicles now, they are automated and connected devices that produce just a plethora of data that we can take advantage of and use to learn about the vehicle over time. And one way that we do that at Liberty is that we develop relationships either indirectly or directly with the companies that manufacture or operate these technologies. So, we have relationships with about 18 of the automotive brands, and we have partnerships with companies like Edge Case Research, and we have other endeavors that I've alluded to throughout the day today that get us access to that data. And we work with those partners to incorporate that data into the underwriting and pricing process. One example is that we have a couple programs out there with a few of the automotive manufacturers that provide some discounting for their ADAS systems. So we have relationships in the space that allow us to get insight into the performance and the changes that occur with those ADAS systems, so that we can incorporate that into the pricing and prove out on an actuarial basis that there's benefit to that. So that's one example, but I think there's others that others might have to talk on.
Thank you for that. And I think it's fascinating that with human drivers, I think our insurance rates tend to go down with experience for a while, and then as our biological sensor systems start to degrade, maybe the insurance rates go back up. But machine learning offers the possibility that perhaps the longer a vehicle's on the road, perhaps the smarter it gets, and the fewer accidents are possible. Let's move now to Sagar. It's widely acknowledged that the methods of safety analysis have served us well so far, but do not necessarily apply to machine learning. So how can safety of automated driving be approached when it is so reliant on machine learning for crucial functions like perception?
So in terms of approaches to safety of AI-enabled systems, there are two main possibilities, both of which are vigorously being pursued. The first possibility is, how can you solve the problem? And the second one is, can you bypass the problem? And when it comes to solving the problem of safety of machine learning, there is a bunch of fundamental science and mathematics that still needs to be invented. So take, for example, some of the methods that are used in a safety assurance exercise for traditional systems. If you're developing software, you will do something that is called MCDC coverage, or you look at cyclomatic complexity of your code, and what does MCDC coverage even mean for a deep learning network? It actually is completely inapplicable. And so there is a lot of research that is going on to address safety for machine learning itself, and it broadly focuses on three areas of validity of the training data, diversity of the training data, and explainability and repeatability of the machine learning network. And there's a bunch of really good stuff happening there, but it is not yet ready for prime time. That's about solving the problem. Bypassing the problem is essentially about taking a systems view. If you have a large and complex architecture with a number of components in it, and if one or a few of those components are machine learning, safety, black boxes, it is still possible to architect systems so that the impact of an error in the machine learning part is bounded. And you can bound that impact and therefore make statements about the safety of the overall system. And to give you a very simple example, let's say a car is driving up to an intersection and there is a pedestrian or a bicycle that is going to cross across the path of travel. Much before you come up to the intersection, if you just forward propagate using Newtonian mechanics, you will assume that the two objects are on a collision course. But as a human driver, you have a lot of context in your head. You know that it's an intersection, you know that the light is green, you know that you have right of way, you are expecting the other party to yield, and so you don't immediately slam on the brakes. And all of this involves a lot of machine learning and is uncertain, and it's difficult to make comments about safety. But we do that because it yields a lot of superior performance. But as the two objects get closer and closer, and if you have sensors like LiDAR that Liam has mentioned, you can use non-machine learning techniques to basically reach a conclusion that solid object about to meet another solid object in the next 3 seconds. And you can take evasive action, you can honk your horn, you can slam on the brakes, you can rotate the steering, and that might not require machine learning to the same extent. So if you have a system that uses a combination of machine learning and non-machine learning techniques, you can engineer a system that is safer overall, even though you're not able to make mathematical statements about the safety of one small part of the system that uses machine learning.
Sure.
I think it's a fantastic answer, and it kind of is pointing out, I think, an opportunity for collaboration both within organizations, so within the broader Toyota organization in your example, or with other stakeholders in the industry. And that is that, what I hear in that is that you're talking about ways using machine learning to mitigate risk. And I think it's worth pointing out because it's something that's intuitive, but it is, I think, often forgotten that the insurance industry is one form of dealing with, going to the insurance industry, working with an insurer is one form of dealing with risk. And organizations that have risk managers or that have risk management practices, they're thinking about 4 ways to deal with risk. They either accept it, they avoid it, they mitigate it, or they transfer it, which would be where they would be giving it off to an insurer, or maybe they have a contractual arrangement that offloads the risk. But yeah, I guess the thing that's baked in there is that there seems to be a real opportunity here, and I'm sure some are taking advantage of it for folks, mitigating risk in the automotive industry or in other industries that are represented in the room to work with their business and risk management counterparts within their organization or with their partners in the insurance industry or regulators or others to explore how they can optimize that mix. So how can you, mitigate risk in one way, accept it in another way that is reasonable, and then maybe transfer it or avoid it completely in other ways? I just think that's a framework we think about a lot when we're talking to our primary clients at major companies, the risk managers, and I think it seems like it's a really big opportunity for collaboration between the technical side of the business and the sort of financially minded side of the business as well.
Thank you. We have a lot of questions coming in from the audience. This is a very interesting panel discussion, it seems for sure, so thank you for all the questions coming in. Let's try and grab a couple of these before we run out of time here. One topic that we haven't really touched on yet is, to what extent is infrastructure changes part of the strategy, or even what role does infrastructure play? Does anyone want to take that? Thanks, Liam.
I'm so glad that you asked that, actually. I just want to talk about, first of all, the automotive safety. While the number of accidents per vehicle mile traveled has gone continuously down for the last 50 years, in the last decade, we've seen a very sharp uptick in pedestrian fatalities. Now, I can speculate to the reason for that, especially if you have a child with an iPhone. But the fact is, it's actually reached quite startling levels. And cities are very concerned about this. And while ADAS systems in a car will help the occupant of the vehicle survive, cities are interested in using infrastructure like LiDARs and cameras at intersections to provide not just data, but also advanced warning. And think about that. Wouldn't that be nice if either in your highly automated car or even a human-driven car, you can get a warning that as you go around into this blind corner, there is a pedestrian behaving erratically. Or if you're exiting a very narrow roadway, sometimes in these narrow roadways, they're equipped with mirrors so that you don't have to stop and you can actually exit with more efficiency. So that's the real function of infrastructure, is it's a way of extending our virtual sensor range. And not only do we get an extension of range, but it's quite possible we will get a reduction in cost, because now we don't need to size our sensors on a vehicle for the absolute worst case situation it's going to encounter. Consider instead that the worst case intersections can be covered by infrastructure, and that information can be shared. And that then allows vehicles to carry sensors for the average case. Now, the question, of course, comes to what if your infrastructure is unavailable? I mean, that's a good question. What do human drivers do if you get to a blind intersection? You don't shoot through it at full speed. You very carefully edge out. So any vehicle working with infrastructure is still going to have some cautious baseline to negotiate an intersection or other area safely, but it would not do so as efficiently as if it had that camera looking around the corner.
Thank you. So a question just came in. I think this one's going to be a bit difficult to answer, but I like the question. How many driving situations or scenarios do companies need to test their systems on before it is safe for deployment? Anyone want to put a particular number on there, or maybe even an order of magnitude? I think that one's going to stump us here. Oh, okay. Thanks, Mike.
I mean, there's definitely not a number, right? I mean, again, this is about there's not a fixed number. I mean, there is a number at some point, right? But I think ultimately what we're trying to get at is what is that correlation between your test plan and the real world scenarios, so that you can say something about what the rates of losses are going to be out in the real world. So I'm dodging the question a little bit because, how do we even define scenario? That's actually a really central question to a lot of the work that we do with our customers. If you think of scenarios as, the motion of idealized vehicles on a road in front of you, then maybe you don't need that many scenarios. I mean, if you're using RSS, you don't need to test scenarios. You can formally verify that it holds, and then, maybe you're good. But, what if we have, instead of idealized vehicles or idealized pedestrians, what if we look at the impacts of, unusual pedestrians and gaps in our machine learning system and difficult environmental conditions? And when you start to try to incorporate all that, you get to more and more complicated scenarios, and that's really one of the centralized challenges here. So I think a lot of the answers are in solid systems engineering on the driving technology itself, paired nicely with intelligent limitations on what's called operational design domain, where you say, well, look, I've limited things in such a way, and I have statistical arguments about these routes or these times of day and things like that, and we've verified that, and we're monitoring those assumptions, and we've built our system right. And so ideally there we would make the number at least feasible and cost effective.
Just add a little. So this is something that, I as a systems engineering guy in this domain think a lot about. And the problem with scenarios is that there is always one more scenario. And one of the reasons why this is such a tricky question to answer is because we don't create this technology so that it is universally operational from time t equal to 0. every single automated driving system that is being developed today is being developed for something that our government calls an operational design domain. Under what conditions is this technology allowed to operate? The number of scenarios you would need for a straight 1 kilometer segment that you will drive with a barrier to oncoming traffic only on sunny days between 12 in the morning and 2 in the afternoon is very different from something that has to deal with rain and fog and slippery surfaces. So the context in which this technology will operate really dictates the scenarios. And this is almost an NP-hard problem. Given a set of scenarios, you can't easily design a solution, but if you have a finite number of scenarios, you can take any solution you have and see if it meets every one of those scenarios. And that is something that companies are doing. But another approach is to ask yourself, what are distinct categories, so that if we can show that these properties hold, I don't need scenarios. So I'll leave you with a little thing to think of. Something that we've always liked to say, because it's a nice sound bite, is in my team, we say, if you don't leave the road, don't hit things, and don't get hit, you're going to be safe. And superficially, it seems like, yeah, what else could be there? But think about it. I know plenty of scenarios where you don't hit things, don't get hit, and don't leave the road, and are horribly, horribly unsafe. So.
Thank you. And for our,
John, I just wanted to add one more point,
Yep.
just to dovetail on that. And I think that, so the companies you mentioned, they're doing different things, right? So a company, it depends on where they are. I think the panel members mentioned operational design domains. That's one of the part of the frameworks that we use. The companies have to describe to us what are the specific areas that these vehicles are going to be operating under. Is it going to be nighttime, daytime, weather conditions, those kinds of things. But also, what is the business model that the ADS is going to be leveraged for? For example, is it going to be neighborhood electric golf carts delivering groceries in just a small geographic area? Is it going to be delivering packages in a very highly densely urban environment? Is it going to be a deployment of a high-end level 3 highway driving system that's only operating on highways? So I think the operational design domain, as we have it, really kind of sets those parameters. And I think when a company comes to us and when we're going to be working with the companies, they're going to have to describe those scenarios as it relates to how the actual technology is going to be deployed out in the public.
Wow, we've had a great discussion, and I feel we're just scratching the surface of some of these topics. But for the final question here, I'm a Parapelli, asked the question that's on everybody's mind. When do we get to buy fully autonomous vehicles? How many more years? How far is the technology in that direction? So,
I'm going to defer to my good colleague at Toyota.
When I defended my PhD many years ago, I did a quick research survey on the first mention of an automated or autonomous vehicle. And I found a reference in mythology that was older than 2600 BC. And I believe that everybody has been saying they're just around the corner since 2600 BC. What I will tell you is there's never going to be a moment in time when they are, click available. This thing will roll out in a series of technological increments. We've started seeing that right now with AEB, with lane keep assist, with level 2 supervised traffic jam pilots. Automated technology is making its way into our streets. The real question is, when will we have technology that will allow us to go to sleep? And again, it will not come out in a universal way. It might come out on that stretch of road and then that additional stretch of road. So the answer is it's already happening, but there is no clear point when we can say, hey, voila, now everything is autonomous.
very good, and thank you, panelists. Very interesting discussion we had. Thank you, audience.